Thank you very much for inviting me to give this talk. And my name is Karin Karlfeldt, Fedje, and I will talk about if municipal solid waste incineration fly and bottom ash can be used in constructions while we're recovering zinc. And I work at a company called Renova. It's a municipally owned company in southwest of Sweden, as you can see on the European map here. And we have activities from collection of waste to landfilling of waste. And I'm also work as a young professor at Chalmers University of Technology. However, one of the activities we have at Renova is waste incineration. And in this plant, we incinerate municipal solid and industrial waste. And we have a mass-burn combustor system. And this generates about 100 ton bottom ash and about 15,000 ton of fly ash every year. The treatment of today for bottom ash is that we have all conventional metal sorting and aging. And thereafter we have the aged and sorted bottom ash that is used for construction purposes, mainly within landfills. The use outside landfills in other applications is limited. But there are examples of constructions outside landfills. And one reason to this is that even though we sort out metal pieces, there are still a lot of metals bound in different chemical compounds present in the bottom ash. And as you know, we have high demand for more metals in our society. So what about if we could recover those metals? Then we would contribute to a more circular economy as we reintroduce those metals into the cycle again. But we would also get a cleaner bottom ash with less metals present, and that could potentially contribute to more activities than constructions within landfills. So how to do if you should recover chemically bound metals? Yeah, the most common ways are hydrometallurgy or pyrometallurgy. Hydro means leaching actually, and pyro means heating it up. And both of these have some disadvantages. For the hydro, for instance, you need a lot of leaching agent. And as the ash is such alkaline, it could be hard to recycle the leaching agent in case you use an acid, for instance. That's the most common one if you leach ash. And for the hydrometallurgy, of course, you need a lot of energy. So it's very energy intensive. An alternative could be phytoextraction. And what is phytoextraction? Yeah, I guess many of you are familiar with this, but it's actually when you use different plants to extract certain compounds from different bacteria. And if we take here as an example with sorted and aged bottom ash. So from now on, when I talk about bottom ash, I mean the sorted and aged fraction, not the fresh one. In that case, I'll say so. However, we pick some plants that we think have affinity for specific elements, grow them or cultivate them in the bottom ash. The metals are extracted by the plants. And then we harvest the plants, and at the same time, we hopefully get a cleaner bottom ash with less metals present. But what do we do after the harvesting? We cannot really put the plant in the landfill because then it will come back again. So we have actually a solution to this, and that is we could incinerate the plants. Because right now, we are building a full-scale plant for zinc recovery at Renova. Because we know that if we incinerate the plants that are enriched in the metals, the majority of these metals will be enriched in the fly ash. And then we treat the fly ash in this plant for zinc recovery, and finally, we could do new zinc products, for instance, nails. So, why did we choose zinc for this plant? Yeah, to start with, we have rather high amount of fly ash in the sorry, we have rather high amounts of zinc in the fly ash, and it's really easy to release. So that's why we start there, but potentially we could extract more metals in the future, and I think that would be the direction for this. But right now it's focused on zinc. And I will come back to that plant, how it works later on, but first I will talk a bit about this phytoextraction of bottom ash. So we did an initial study where we had the goal to first see would the plant survive at all, actually, and could we generate a metal-enriched fuel with focus on zinc, and how clean would the bottom ash be? We didn't find any other study published in any scientific journal where they have been working on conventional bottom ash. There is another study, but they have pre-treated the bottom ash. So we didn't actually know if it should survive. We also had some prerequisites on the plants, and it was that it should be open to cultivate it on open land in a Nordic climate. Many of these hyper-accumulators, as these kind of plants are called, grow in more temperated climates. We also would like to harvest within one cultivation season, because as we didn't know if this should work, we decided to start with a rather short project. We wanted the plants to have high affinity for zinc and that the relative biomass should be significant. And after we have done literature review and so on, we ended on sunflower and rapeseed. So what did we learn from this project? Yeah, the plants actually survived in the bottom ash. The sunflower was dried after a couple of months, while the rapeseed survived rather nicely, actually. We also detected enrichment of metals in the plants, especially in the roots, but the cleaning of the bottom ash was limited. Additionally, we realized that the addition of nutrients is very critical for good cultivation, and also the addition of humus or other organic material that could contribute to better capacity for holding nutrients and water compared to if only the bottom ash was used. Thick roots of the plants is another advantage because the bottom ash is rather dense, and if you have weak roots, it's hard for them to penetrate these materials. And we also think the perennials is better because as you have such high content of metals in the bottom ash, it will not be extracted during one cultivation season. You have to wait for a longer time. So with this new knowledge, we decided to start a new project, and it's a PhD project started in August last year. And here we will build different kinds of filters, where one of the materials that we will use in the filter is bottom ash. But we will not water with fresh water, but with urban runoff. And this urban runoff water comes from one of the most trafficked highways in the Gothenburg region. So it's contaminated not only with metals, but also with organic pollutants and microplastics. And to some of the pilots, we will also add mycorrhiza to try to promote the growing of the plants and the extraction of the metals. So what we hope for here is that we will have the same practice as we could see in the previous project, that metals, if we talk about the metals here, are extracted by the plants, and then we can harvest the plant and recover the zinc in the first stage, and that we will have a cleaner bottom ash material. And for the other pollutants, the organic pollutants and the microplastics, it could be that they are degraded during the process or that they are extracted by the plants as well. So depending on what happens to them, it could be that we treat them before we incinerate the plant, or they are incinerated together with the plant. So as you see here, it's a pollution cocktail that we deal with, and that means that we will have a combination of plants where each of these plants are focused on different pollutants. And we think that for the bottom ash and the metals, the sea buckthorn is likely the most efficient plant. But we will see that. We will start up this spring with the first cultivation season, so this will be really interesting to follow. So let's go to the zinc recovery process. And here you can see a photo from the building of our full-scale plant, and it will be up and running in May this year. This is a unique plant. I don't know any other plant that will be operated exactly as we do. And when we are doing this in full scale, we will generate about 200 tons zinc every year. And just to get you an idea, between the thumb and the finger, it's about 500 million nails. So we could not close down all the zinc mines we have, and that's not the meaning of this either. But still, it's some zinc generated here that we could utilize again. And by doing this, we contribute to the circular economy, and it will be less costly for us to treat the fly ash when we do it this way, and we will decrease the need for landfill. So how does it work? Yeah, the principle is rather easy, actually. We use electrostatic filter ash, and then we take acid from our wet flue gas cleaning. We mix these two together, and then we generate a metal-rich leachate. And from this leachate, you can generate high purity zinc metal. However, this large step here is rather complex and costly. So we decided to, instead of going the whole way to high purity zinc metal, generate a zinc product. And this zinc product should be good enough for the metal industry to treat it. And that means it should be high in the elements that they want to have and low in the elements they don't want to have. And that's the reason why you can't take the ash directly to treat in the metals industry, because the ash contains so many different elements that could harm the processes. So we take this way, washing, precipitation, and a zinc product. And for this part, we have 70% of zinc recovery. So that's really nice. And we had the same results when we did this in laboratory scale as in pilot scale. So we hope it will be the same for the full plant. Concerning the ash residue here, that's separated from the liquid, you could either treat it further to try to extract more metals, or you could maybe re-incinerate it to get rid of the dioxins that's present in the fly ash. It could maybe be landfills or something else. And in our project, we decided to study this re-incineration a bit further. And as I said, it's to degrade the dioxins, because the dioxins aren't released during the washing process. But instead, if you re-incinerate washed ash, fly ash, it will be converted to bottom ash. So instead of landfilling or doing something else with the fly ash residue, it could be converted into bottom ash and maybe used in constructions. And this has been tested, for instance, in Germany and Switzerland with good results, but we would like to do it on our own plant, of course, to see what happened. Would it be some changes in the bottom ash if we did this? So we tried in 2 full-scale experiments to re-incinerate the washed fly ash, and we could see that more than 90% of the incinerated fly ash was converted to bottom ash, to fresh bottom ash. We also saw it was similar amounts for most elements with or without fly ash re-incineration, but for some elements it increased and some it decreased. But we couldn't say that this was due to the fly ash addition or if it was just natural variations. So, but it seems that it's due to natural variations, but we have to evaluate this even more when we are up and running at full scale. But the conclusion here is that if we do like this, we could actually extract zinc from the fly ash and then convert the fly ash residue into bottom ash, and that could be used in construction. So to sum up this, today the bottom ash is used within landfills in Sweden in majority of the cases. Metal recovery could potentially promote bottom ash utilization as we decrease the metal content in the bottom ash, and phytoextraction might be a way to do this that we are studying right now. And concerning the way of the metals, we have them in the bottom ash. We cultivate plants that extract metals, we incinerate the plants, and the metals are enriched in the fly ash. And from the fly ash, we can today recover the zinc that's present in the fly ash. We have about 70% efficiency in this recovery process. The fly ash residue is converted to bottom ash, and this leads to decreased landfilling and a less costly fly ash treatment. And last but not least, we contribute to a circular economy in a good way. And hopefully in the future, we will be able to recover more metals from the ashes. If you would like to read some more, there are two published papers, one about the initial study on phytoextraction and one about the zinc recovery plant. So thank you very much for your attention.